In this video, we're going to look at the naming system of the final functional group produced by a dehydration synthesis reaction, that being the amides, which, not surprisingly, are identified by the suffix amide, which we can take a look at by looking at this relatively simple amide compound that we see here. Now, the first stage in identifying the name of any organic molecule is to identify which part of the molecule is the parent chain, because that's going to be the root on which we build the entire name. Now, we identify the parent chain of amide compounds the same way that we do with esters, by looking for the half of the molecule that used to be the carboxylic acid half. So if we divide our molecule into A halves and B halves here, we can see that the A side used to be the amine, because we can see the nitrogen is over here, whereas the B side of this molecule, we can see the carbon that contains our amide functional group contains the double bonded oxygen, and therefore this is the side that used to be the acid. So if we count carbons, we can see that the hydrocarbon that is the basis for our parent chain is going to be bute. We see there are only carbon-to-carbon single bonds, so this would be butane. And then we designate the amide functional group here by adding the suffix amide, and this would be pronounced butanamide, or butanamide if you prefer the emphasis on the word amide. Now, the trick with amides is with identifying the side chain that used to be part of the amine, or that used to be the amine in the two molecules that underwent dehydration synthesis. Now, because this side chain, which we can identify here because it has two carbons, we can identify this as an ethyl side chain here. But the problem with naming this is that it does not directly contact any of the carbons of our parent chain here. Instead, it is attached to the nitrogen that is part of the amide functional group. And therefore, instead of giving this a carbon location like 1, 2, 3, or 4, we give it the location number N to show that this is bonded to the nitrogen atom in the amide functional group that we see here. So the name of this amide here would be entitled N-ethyl butanamide, signifying that our parent chain is 4 carbons long with single bonded carbons and an amide functional group, and that on the nitrogen of the amide functional group we have a 2 carbon long side chain. Now, the general idea of naming amides is that the side chain that is attached to the amide is treated in exactly the same way as you would a normal side chain, just with the location number as being N rather than an actual number. So if we take a look at the two amide examples below, we can actually see that naming amides is relatively intuitive if we just treat this whole section here as we would any other side chain coming off of the parent chain here. So if we identify our parent chain, we can see that the right side of this molecule is the side that used to be the acid, because the double bond O is here. And if we count carbons, 1, 2, 3, 4, 5, 6, we can recognize that our parent chain is a hexane because there are only single carbon-to-carbon bonds, and then we give it the suffix amide to indicate what the functional group is. All that remains is to identify the names and locations of all of our side chains. So on carbons 2 and 5, we see that we have dichloro, meaning 2 chlorines. Then we can see on carbon 3, we have an ethyl side chain here. And then on carbon 4, we have a methyl side chain here, which brings us to the side chain that is located on the nitrogen of the amine. We can see that there are 3 carbons here, and therefore we would designate this as N-propyl to indicate that we have a 3 carbon long side chain that is attached to the nitrogen of our amine. And now that we've identified all of our side chains, the alphabetical order remains the same. So we can start by identifying 2,5-dichloro as our alphabetically first side chain, followed by 3-ethyl because E follows C alphabetically, then 4-methyl because M comes after E but before P, and then finally we have our N-propyl to show that this 3-carbon long side chain is attached to the nitrogen in the amide, and then all that's left is our parent chain name, which is going to be hexanamide or hexanamide, depending on where you want the emphasis. If we take a look at this final example here, this is a relatively quick one. We can see that our parent chain is going to be propanamide or propanamide because we have 3 carbons in the acid side of our amine or of our amide rather, and we have only carbon-to-carbon single bonds, and for side chains we have 1, 2, 3, 4 chloros, so we have tetrachloro, where our chlorines are located, 2 of which being on carbon 2 and 2 of which being on carbon 3, and all that remains is to identify the side chain that is attached to the N of the amide, and we can see 1, 2, 3, 4, 5. This is going to be an N-pentyl side chain. And once again, all that's left to do is alphabetize our side chains. Chloro clearly comes before pentyl, so we would put 2, 2, 3, 3 tetrachloro before our N side chain, and then we would add N-pentyl, followed by the name of our parent chain, which in this case is propanamide or propanamide, depending on your pronunciation. This concludes our series on the structural recognition and nomenclature of functional groups formed by dehydration synthesis reactions. To test your knowledge on recognizing, drawing, and naming these functional groups, you can take a look at the practice problems below, in which you are given reactant pairs and required to name both of the reactants and draw what the product is, identify what functional group is formed, and name the product based on the rules for ethers, esters, and amide naming.